Create transformers components. Embedding layer. The embedding layer converts input into vector representations for efficient processing. This involves tokenization. Breaking down input into tokens, often subword tokens of approximately 4 characters. Integer assignment. Assign each token an integer ID and save it in a vocabulary dictionary. Vector conversion. Converting each integer into a multi-dimensional vector, each token feature is represented by a vector dimension. Transformers have 2 embedding layers, one in the encoder for input embeddings, and one in the decoder for output embeddings. Positional encoder. The transformer generates positional encodings and adds them to each embedding to track token positions within a sequence. Positional encoding approach allows parallel token processing and better handling of long-range dependencies. Self-attention mechanism. The self-attention mechanism is the most crucial component of the transformer, responsible for comparing embeddings to determine their similarity and semantic relevance. The self-attention mechanism generates a weighted input representation, capturing relationships between tokens to calculate the most probable output. At each self-attention layer, the input is projected across several smaller dimensional spaces known as heads, referred to as multi-head attention. Each head focuses on different aspects of the input sequence in parallel, developing a richer understanding of the data. The original self-attention mechanism has 8 heads, but the number can vary based on objectives and available computational resources. The encoder and decoder contain self-attention components. The encoder has 1 multi-head attention layer, while the decoder has 2. Feed-forward network. This layer captures higher-level features of the input sequence to recognize intricate underlying relationships. It consists of 3 sublayers. First, linear layer. This layer projects input onto a higher dimensional space, example, 512 to 2048 in the original transformer. Nonlinear activation function introduces nonlinearity to help learn more realistic relationships. A common activation function is the rectified linear unit, ReLU. Second, linear layer. This transforms the higher dimensional representation back to its original dimensionality, compressing additional information while retaining relevant aspects. Normalization layers. Normalization ensures input embeddings fall within a reasonable range, stabilizing the model and mitigating vanishing or exploding gradients. Transformers use layer normalization, normalizing the output for each token at every layer, preserving relationships between token aspects, and not interfering with the self-attention mechanism. Residual connections. Residual connections feed the output of one layer directly into the input of another, improving data flow through the transformer. These connections prevent information loss, enabling faster and more effective training. During forward propagation, residual connections preserve the original data. And during backward propagation, they help gradients flow more easily through the network, mitigating vanishing gradients. And during backward propagation, they help gradients flow more easily through the network, mitigating vanishing gradients. In the next lesson, I will talk about assembling the encoder and decoder. Stay tuned. Keep learning. Subscribe to our YouTube channel www.codingscientist.com.